Alright, so this video is going to be part 2 of our sequences and series review. This is going to be on convergence and divergence of sequences, and more on sequences like seeing if a sequence is monotonic, if it is bounded, and utilizing the monotonic sequence theorem. Okay, so to start off, the first thing we really talked about with sequences was the convergence and divergence of them. Okay, now if a sequence was to converge, okay, that means that it's approaching a finite value. Okay, something like this, where we have a sequence approaching a finite value, and this would be your a sub n up here, this is your n. Now, why is there a dotted line rather than a line that looks like this? Okay, the reason for that is because your n, okay, your input here is always it's a positive integer. Okay, you're not putting in anything that's not an integer. Okay, so that's kind of what we're talking about now. If it approaches an infinite value, if it looks like this, okay, then it is divergent. All right, so how do we prove if a sequence is going to converge or diverge? Well, we're just going to take a limit, right? We're just going to take a limit as n approaches infinity, and then see, is a sub n approaching an infinite value or a finite value? That will help us to prove if it is convergent or divergent. So we can do an example here. We have a sub n equal to 4n plus 2n squared all over 3n. Okay, is this sequence going to be convergent or divergent? Well, like I said, let's just take a limit here. Okay, let's take a limit as our n approaches infinity. Okay, let's see what happens to our a sub n. So we're going to be taking the limit of our a sub n right here, 4n plus 2n squared over 3n. All right, now we can do one of two things here. We can compare it to a function. We can compare it to the function 4x plus 2x squared over 3x. Okay, what that would allow us to do is use L'Hopital. Okay, we can't use L'Hopital with sequences, and that's just a mess. So, anyways, yes. So we can. That's one of the things that we can do. The other thing that we can do is divide by the highest power of n, that being n squared here. So let's go ahead and do that. If we divide by the highest power of n, which means we're dividing by n squared, we get 4n over n squared plus 2n squared over n squared over 3n over n squared. Now, why did we divide by this highest power of n? Well, it simplifies this down tremendously. We get the limit as n approaches infinity of, well, now we have a 4 over n plus a 2, and that's going to be over, well, that's 3 over n. Now, this 4 over n right here, well, as n approaches infinity, this is basically going to end up being 0. Okay, it's going to be an infinitely small number. Okay, it's going to be an infinitely small number. So we can kind of just cross this off here. It's not going to matter too much. But now we have something a little bit stranger. Okay, we have a 2 over a 3 over n. Now, we're not going to say that this 3 over n is 0. Okay, it's going to approach 0. It's not going to equal 0, just the same as with 4 over n, but 4 over n is going to be insignificant here. Okay, 3 over n is not, and you can even rewrite this by putting it as 2n over 3. It's the same thing. Okay, and it's kind of easy to see here that you have 2 over an infinitely small number, or an infinitesimally small number. That's how you say it. And that's going to give us an infinite value. So this limit is going to equal infinity. So this sequence is going to be divergent. Next, what if our sequence was, well, a sub n equals, where is it here? Here it is, n plus 1 quantity squared over 2n squared plus 3n. Okay, a little bit harder to see, I guess, what's going to happen here because of this n plus 1 in the parentheses. Okay, here you kind of can just tell, okay, we can either divide by the highest power of n or use L'Hopital, but here, well, not so much. But it does become a lot clearer when you take your limit, okay, your limit as n approaches infinity, if you distribute this out, or you FOIL it out, that's the right word. We get n squared plus 2n plus 1 over 2n squared plus 3n, and now it's a lot easier to see what's going to happen. Now, because we divided by the highest power of n before, I will also show you how to use L'Hopital for this. We're going to compare this, okay, we'll compare this a sub n to f of x, okay, and f of x is going to be equal to x plus 1 quantity squared over 2x squared plus 3x. Off of that, we're going to end up taking the limit as x approaches infinity of x squared plus 2x plus 1 over 2x squared plus 3x. Now, really, we don't care about 2 or the 3x here or the 1, because we only care about the highest powers of x, which is, we have an x squared on the top and an x squared on the bottom. We care about the coefficients in front of those. So you can see here that there's a 1 here and a 2 here. Our limit's going to end up equaling 1/2, but I'm going to show you that with L'Hopital real quick. Okay, just if it's ever not clear for you at all. If we use L'Hopital, our next limit is going to be, well, remember what L'Hopital says, okay? We have to have a case like an infinity over infinity or over 0 over 0, something like that, okay, in determinate form. And then we can take the derivative of the top separately from the derivative of the bottom. Okay, so here we go. We get a 2x plus 2, and that's going to be over that's going to be a 4x plus 3. Again, if you look at this limit, you don't care about anything that's not the highest power of n here. We do care about the 2x and the 4x, but we don't care about the 2 and the 3. Okay, so again, we would get our 2 over 4, which is 1/2. So we still have the same thing here. Now, just because I said I wanted to use L'Hopital in this problem, let's do it one more time. And we get the limit as, these are supposed to be x's, x approaches infinity of, we take the derivative of the top, we get 2, take the derivative of the bottom, we get 4. Okay, and that is equal to 1/2. Which means that this sequence right here converges to 1/2. Notice that you can say what it converges to with a sequence, okay, but when we get into series, that's not going to be the case, okay? It's not that easy to see what it converges to, all right? So real quick here on the other stuff that we learned on sequences, we were talking about a sequence being monotonic and bounded and what it means for a sequence to be monotonic, because I guarantee, it was something that popped up on my test for sequences in series, so I assume it will pop up on yours too. A sequence is monotonic if it is strictly increasing or decreasing. Okay, so something that looks like this, or something that looks like this, okay? Strictly increasing or decreasing. Now, a sequence can be bounded above, bounded below, or it can just be bounded, which means it's bounded above and below. Here's an example of a sequence being bounded above. Okay, if something happens like, let's say that we have something like this, okay, and we have that this sequence, okay, will never touch this line. Let's call it a sub n equals k. Okay, it will never touch that line. That means it's bounded above. Now, what about bounded below? Okay, let's do bounded below. Now, bounded below is basically saying the exact opposite. So maybe the sequence is starting up here, okay, and maybe it flattens out here, and it's never going to touch this line. Let's call that a sub n equals m. Okay, it will never touch that line. And what that means is that this sequence is bounded below. Now if a sequence is bounded, what that's basically saying, you might start out here, okay, and you might have something like this. Say we have something that kind of looks like sine here, and you have that your sequence won't pass either of these two lines that I just drew here, a sub n equals k and a sub n equals m. Well, this sequence is bounded then, okay? It's called a bounded sequence. And then you have the monotonic sequence theorem, okay? Every bounded monotonic sequence is convergent. Now let's say that this represents a sub n equals sine of n. You cannot use, actually this would be sine of n plus 1. Let's say sine of n plus 1, because it's not, sine of n would start from there. Anyways, you can't say that this is convergent by the monotonic sequence theorem because it's not monotonic, okay? It's not strictly increasing or decreasing, okay? It's doing both. So, but it is bounded, okay? So let's do a quick example. Now what you would kind of get with something like this is a question like this. Is the sequence increasing, decreasing, maybe both? Is it monotonic or not monotonic? Is it bounded? Is it convergent or divergent? You'd just be asked a bunch of questions. I think that's a very likely thing to have happen for a question on sequences. So here we're given the sequence, a sub n equals 1 over 2n plus 3. Okay? Now first, how do we check if it's going to be increasing or decreasing? Well, let's look at the next term in this sequence. Okay? Let's look at the next term in the sequence. That would be, well, that's going to be a sub n plus 1. Okay? A sub n plus 1. And a sub n plus 1, all I did here was I plugged in a n plus 1 for n. Okay? So if I plug in n plus 1 for n in our actual sequence, we have a 2 times n plus 1 plus 3. And that's going to be equal to a 1 over 2n plus 2 plus 3, which is equal to a 1 over 2n plus 5. So, compare this to 1 over 2n plus 5. Okay, this is our a sub n plus 1. Is this greater than or less than our 1 over 2n plus 3? Okay, well, since the denominator is larger, that means that this is going to be smaller than this. So we can write this. Okay, now you may be wondering, well, how do I know now, like, what does this mean? Well, this means that our sequence is decreasing, but you may also be wondering, how do we know that it's decreasing for all n? Well, that's because right now we're using n's, okay? We're not plugging in numbers, we're not looking at a specific case, okay? We're realizing that since we're using this variable, okay, 2n plus 5 will always be greater than 2n plus 3. Okay, and that's going to keep happening. Okay, if you try n plus 2, n plus 3, n plus 4, that's still going to happen, and you're going to get a decreasing sequence. Okay, so now we know that it's decreasing. Okay, we know that it's decreasing now. So we can kind of, let's write that right here. Decreasing. And is it monotonic or not monotonic? Since it is strictly decreasing, we know that it is monotonic. Now, is it bounded? Well, let's take a look at what this would look like. Okay. Now, I'm going to admit, I don't know exactly what this graph looks like, okay? But I do know that it's going to look something like a 1 over n graph. Okay, it looks pretty similar to that, right? I mean, we're just multiplying a number and adding a number. So really, it's going to look a lot like 1 over n. So let's say that it looks like this. And notice there's not going to be an asymptote here because we're starting from n equals 1, right? We're only using positive integers. We're not using 0.001 to see that this would be an asymptote, okay? So since it's strictly decreasing, it's not going to get any bigger than this first point right here, which I'm going to call, let's call that k, okay? A sub n equals k. It's also not going to get any smaller than a sub n equals 0. Okay, a sub n equals 0. Now what's k? Well, let's plug in n equals 1 and find out. If we plug in n equals 1 here, yeah, that gives us a 1 over 2 times 1 is 2, plus 3 is 5. So this k is going to equal 1/5. So we can write here that a sub n equals 1/5. Okay, so we can write that the sequence is bounded by, let's call this, let's say 0 is less than a sub n is less than or equal to 1/5. Okay, so this is, it is a monotonic sequence, it is bounded, so we know that it's convergent by the monotonic sequence theorem. And right there, that is our answer, right? So yeah, that's about it, and that's going to do it for this video. So if this video helped you, make sure to leave a like and subscribe by clicking my icon in the top left. You can also view the playlist for sequences and series and the next video in the series. Lastly, if these videos are really helping you and you would like to consider supporting me, I have my Patreon linked in the description down below, along with some other pretty cool links that you should definitely check out. See you soon.